In the late 1940s, a team of scientists from AT&T Bell Labs invented a device called a transistor. This is a three-terminal device made from a semiconductor and replaced the functionality of a larger device called a triode that is made from vacuum tubes. The invention of the transistor led to the advancement of other devices like the integrated circuits and eventually the invention of the microcomputers. In the picture in front, we can actually see an example of transistors. So these are transistors, and these are ICs that are made of thousands or even millions of transistors. So in this module, we're going to discuss the construction, operation, and application of transistors, and how they are used in some specific applications like amplifiers and switching. The objectives for this video are the following. We will show the construction of bipolar junction transistors. So we'll be focusing on BJTs uh, because there's another type of transistor called FETs, the field effect transistors. So we will not discuss FETs, but we'll just focus on BJTs. We'll also describe the different connection configuration of transistors. Um, we will show some input and output characteristics of common emitter configurations and describe how to test a transistor. A transistor is a three-terminal device made of three layers uh, of P-type and N-type materials. There are two types of transistors. We have the PNP and the NPN transistor. A PNP type transistor is made from one N-type material that is sandwiched by two larger P-type materials. So we can actually see the relative thickness of these materials as shown here. Access to the layers are done by connecting a conductive terminal to them. These terminals are called the base terminal, that is the connected to the center layer of the transistor, and the other two outer layers are connected to terminals labeled E for emitter and C for collector. This is the symbol of the PNP transistor. The emitter and the collector are distinguished from each other by the fact that the emitter contains an arrow that is pointed inwards if we're talking about PNP transistors. An NPN transistor is made from a P-type material that is sandwiched by two larger N-type materials. And again, the terminals are labeled as emitter, base, and collector. So again, the center layer is labeled as the base. The emitter and collectors uh, are distinguished from the symbol by the fact that the emitter again contains the arrow that is pointed outwards if we're talking about NPN transistors. We also have an actual picture here of a transistor. There are many more depending on the package of that transistor. One of the most common application of transistor is in amplification. So that is if you have a circuit, for example, that contains the transistor, and the function of the circuit is for amplification. So we call this circuit an amplifier. So this circuit takes a weak signal, and that signal is transformed into a larger version of the input signal. Now, amplification functions can be accomplished using three of the available transistor configuration. These configurations are called the common base, the common emitter, and common collector configurations. One of the transistor configuration used in transistor-based amplifier is what is known as the common base configuration. In this configuration, the base of the transistor is actually common between the input and the output of the amplifier. The input is the input enters the emitter base terminals, and the output is taken from the collector and base terminals. In actual operation, the emitter base junction, which is this one, is actually forward biased. So in this picture here, the voltage V sub EE is actually forward biasing the emitter base junction because the P-type material is connected to the positive, and the N-type material, which is the base, is connected to the negative of V sub EE. So therefore, this junction of the emitter and base is actually forward biased, while the collector base junction is reverse biased. So the voltage here, V sub Cc, actually reverses bias this junction because the base, which is an N-type material, is connected to the positive of V sub Cc, while the P-type material uh, of the collector terminal is connected to the negative side of V sub Cc. Uh, so this is for the PNP type, and this is for the um, NPN type. Now, in a properly biased transistor, a small current between the emitter and base terminals. So, for example, we have a small current that flows between the emitter and base will actually result into a larger current from emitter to the collector terminal. So we have the same scenario there for NPN transistor. So a small current from the base to the emitter terminal will result into a larger current from the collector going to the emitter. And this is illustrated by these arrows here on top. For a common collector configuration, uh, again, the collector now is actually the common terminal. So this is the input here, and this is the output here. Okay, and the input enters the base and the collector. Okay, so it enters this base and collector, while the output is taken from the emitter and the collector. Again, in actual operation, The base collector junction, which is this one, which is the base collector junction, is actually forward biased by a voltage, and the um, emitter base junction, okay, emitter base junction is reverse biased. Again, in a properly biased configuration, a small current between emitter and base, so we have a small current going there, will turn into a larger current between emitter and collector in that direction. Okay, illustrated by this one. For NPN, a small current from here to there will actually result into a much larger current between the collector and the emitter, so as shown by this one. We also have the common emitter. This is one of the most popular configurations. So here we have the emitter being common between the base, between the input and the output here. Okay, so this is the output. The input enters between these terminals, base and emitter, and the output is taken between the collector and emitter terminals. The base emitter junction is forward biased, so this is the base emitter junction. This one is forward biased by this, while the collector base, which is this one, is reverse biased. In this configuration, a small current circulating between the base and emitter will result into a large current from the collector going to the emitter. So let's talk about the common emitter characteristics. So there are actually two curves, family of curves um, for every transistor configuration, and we'll only talk about the characteristics of common emitter configuration. So for a common emitter, so the common emitter would look like this for a NPN transistor. Okay, so this would be the base, the collector, and the emitter. Okay, so so the base or the input characteristic is a plot between the base current. So we have here the base current and the base emitter junction. So this is the base emitter voltage, so BE, for a given collector emitter voltage. So this is VCE. Okay, so this is the plus here, minus, plus, minus. So as you can see, this is a family of curves, and the plot is actually similar to the plot of a diode, because since this one is actually an N material and this is one is a P material, and it is like um, um, and this is also an N material, so this is like a the base and emitter junction is like a diode actually, and so this is like a diode. Okay, So if you're going to get the characteristic between I sub B and VBE, you will get a curve that looks like the diode characteristics. But it is a family of curves because the actual curve, although similar, depends on the voltage across terminal C and E. We also have the collector or output characteristics of the common emitter configuration. This is also a family of curves, and this is a plot of the collector current versus the collector emitter voltage for a given base current. So for example, if we have a base current of 30 microamps here, that would be the curve, the output characteristic curve here. Okay. Now in this family of curves, we have uh, three regions. We have what is called the cutoff region, this one. So this is the cutoff region. We have the saturation region, so this area here, and we also have the active region, which is, well, it is this region here, that is the active region. And this is the region where the transistor usually operates, especially if it is used as an amplifier. In the common emitter configuration, the collector current is approximately proportional to the base current. Writing that as an equation, we can write it like this, where the constant of proportionality is given here as beta. It is called the DC amplification factor for this configuration. So the DC amplification factor is actually the ratio of the collector current and the base current. And usually this is much greater than 1. Okay? So let us have a simple example to illustrate um, the output characteristic. Here we have the output characteristic, and we are to determine the amplification factor beta at V sub CE equals to 7.5 volts. So that would be in this line here. Okay, so this one is 7.5 volts for a base current of 30 microamperes. So that would be this curve here, and 20 microamperes. So that would be this curve here. So for base current equals to 30 microamps. So this is for 30 microamps. IB, the beta would be I sub C at 7.5 volts of V sub CE, and that would be this one. Okay, so it's here, so it's about 3.25 milliamps because I sub C is given in milliamps. We divide that by the base current, that is 30 microamps, and we will get there 108. So this is dimensionless. Now for an IB equals to 20 microamperes, so that would be this curve, and this will be this point here, and that will give us this one. So that is around 2.25 milliamps divided by 20 microamps. That will give us 112 uh, as the DC amplification factor. So they are pretty close, and in an active region, the amplification factor is roughly constant um, and sometimes affected by the temperature of the transistor. It is actually important to know whether a transistor is in good working condition or broken. So this can actually be tested using an ohmmeter. So an ohmmeter is a device that tests the resistance of a resistor, but it can also be used to check the condition of a transistor. Now here we have an NPN type transistor. So if we connect, for example, the positive of the ohmmeter to the base and the negative to the emitter, if this is a good transistor, we should be able to get a very low resistance reading. Okay, so that is only half of the check, and the other half is if we connect the positive again of the ohmmeter to the collector and the negative to the base, we should get a very high resistance reading, and that would indicate a good uh, transistor. Any reading that is contrary to the above will tell us that the transistor must be faulty and should be replaced. I've listed here some common applications of transistors. So these are the switching applications, power supply, amplifier circuits, and in logic gates. Here we have a transistor circuit that is used as an AND gate. So an AND gate is a device that takes two inputs and outputs one output. Okay, this is the truth table for this gate. So a truth table shows the combination of the two inputs and the resulting output. So here we have if the input is 0 and 0, so this is 0 here and 0 here, the output would be a 0. So what do you mean by this? So for example, if my input in A is uh, 0 volts and my input to B is also 0 volts, that means what will I get here is an output that is also 0 volts. Okay, if my input in B is 0 volts and my input to A, for example, is 5 volts, okay, so that means it is a 1. Okay, so here it is still 0. I will still get an output that is 0, which is 0 volts. If my input to A is, let's say, uh, 5 volts, again 5 volts, that means it is a 1, and or I mean 0, 0 volts, so this is a 0, but my B is 5 volts, so this is 1. I will still get an output that is 0 or 0 volts. Finally, if my input to A is 5 volts, so that is a 1, and for V it is also 5 volts, it is also 1, and that's the time I will get an output that is a 1 or a 5 volts. Okay, so that is how an AND gate works, and this is the circuit to implement that AND gate using two transistors. The drawing on the right is actually a simple amplifier. So this is the input signal here, So it goes to the uh, so this uses a common emitter configuration. So the signal will pass through the capacitor going to the base, and the output is actually taken across the collector. So this is the collector here, and that you will get a very large signal depending on the amplification factor of the transistor.